Have you ever stopped to think about what's really going on inside the cable that's charging your phone right now? Probably not, right? But the answer is pretty incredible. Today, we're going to pull back the curtain on one of the most fundamental forces that powers our world, electric current.
Seriously, just look at any wire or cable you have nearby. It seems so still, so boring. But if you could shrink yourself down to the size of an atom and go inside, you would find a world that is anything but still. It's a hidden universe of constant, chaotic motion.
So let's do it. Let's zoom way in, past anything a microscope could see, and take a look at the structure of a metal like copper. You'll see it's not quiet at all.
So, what makes a metal a good conductor? Well, it's packed with what we call free electrons. They're not tied down to any one atom. They're like a giant sea of particles just free to roam. And because of thermal energy, just the heat in the room, they are in a constant state of motion, zipping around like crazy in every possible direction. It's total, absolute, microscopic mayhem.
But here's the thing, and this is super important. Even with all of those electrons moving around frantically, we do not have an electric current yet. Not at all. Why? Well, because the movement is completely random. For every electron heading left, there's another one heading right. For everyone going up, another's going down. It all just cancels out. There's no overall flow in any single direction. It's all a wash. So, how do we turn that useless random buzzing into something that can actually power your laptop? How do we bring a little bit of order to all of that chaos? Well, that is the secret to what an electric current really is.
And this is the magic moment. An electric current is born the second we can get all those free electrons to stop just moving randomly and start to, drift together in one particular direction. It's not that the random motion stops. It's that on top of all that chaos, there's now a slow, collective movement, a coordinated flow. And that is an electric current.
Putting it side by side like this really makes it click. On one side, you've got pure chaos fueled by heat, no current. On the other side, you still have all that chaos, but now an electric field has been applied, causing a tiny, overall drift in one direction. That subtle, ordered drift is everything. That's the current.
Okay, so we've got a flow. Simple enough, right? Well, not so fast. Because now we have to ask, which way is it flowing? And this is where science history throws us a really weird curveball. You'll see diagrams with arrows pointing in opposite directions, and it can get super confusing. So what is going on?
All right, check this out. We know electrons have a negative charge, so naturally they're attracted to the positive terminal of a battery and repelled by the negative one. The actual electrons flow from negative to positive. Makes perfect sense. But way back in the day, before anyone even knew what an electron was, scientists just took a guess. They assumed that the thing flowing was positively charged. So they defined the direction of current as flowing from positive to negative. So why on earth do we still use this backwards convention today in physics and engineering? Well, as our source material perfectly puts it, it's simply due to the weight of history. It's a historical quirk we're just stuck with. The good news is all the math works out just fine either way, as long as everyone agrees to be consistent.
So we have this ordered drift, this flow. The next logical question is, how much flow is there? How do we actually measure the size or the intensity of a current?
And this is where we meet the amp, or as most people call it, the amp. Now, an amp doesn't measure how fast any single electron is moving. Instead, it measures how many charges are flowing past a certain point in a certain amount of time. It's a measure of volume, not speed. Here's a great way to picture it. Imagine you could just plant a little imaginary gate, like a finish line, somewhere inside that wire. To measure the current in amps, you just have to count the total amount of charge, all the electrons, that passes through your gate every single second. A lot of charge per second means a high current. A little bit of charge means a low current. Simple as that.
But when you actually start to count, the numbers are just mind-blowing. A current of just 1 amp, about what a typical light bulb might use, means that 6.24 quintillion electrons are flowing past that imaginary gate every single second. That is a number so ridiculously large, it's hard to even wrap your head around.
Talking about quintillions of electrons can get a little abstract. So, to make all this feel more intuitive, let's use a fantastic, classic analogy that really helps bring it all back down to earth.
Yep, let's just forget about electricity entirely for a moment and think about regular old plumbing. Because the flow of electricity in a wire is incredibly similar to the flow of water through a pipe.
This analogy is a real game changer. The electric current, measured in amps, is just like the flow rate of the water. How many liters are coming out per second? Voltage, which we'll get into next time, is like the water pressure that's pushing everything along. And resistance? That's just like a narrow section of the pipe or a kink in the hose that makes it harder for the water to flow.
Okay, we've spent a lot of time talking about what current is, this massive ordered flow of charges. But we haven't asked the most important question. What is it for? What is the whole point of sending trillions upon trillions of electrons on this journey?
And this right here is the key takeaway. The electrons are just the delivery trucks. The real cargo they are carrying is energy. At its heart, an electric current is an energy delivery system, and it's an incredibly efficient one. So how do they deliver the energy? Well, as those electrons drift through the wire, their path isn't clear. They are constantly bumping into and colliding with the atoms of the wire itself, kind of like a microscopic pinball machine. Every single one of those tiny collisions transfers a little bit of energy from the electron to the atom. Multiply that by quintillions of collisions per second, and that energy becomes noticeable as the heat from a toaster or the light from a bulb.
That constant bumping and opposition to the flow has a name: electrical resistance. And you might think resistance sounds like a bad thing, but it's not. It's absolutely essential. Resistance is precisely how that energy gets converted into something useful. It's the friction in the system that allows the energy to be dropped off and put to work.
So let's bring it all together. Electric current is the ordered collective flow of a staggering number of charges, and its fundamental purpose is to deliver energy. But this leaves us with one last massive question. If current is the flow, what provides the push? What's the force that gets this whole incredible process started in the first place? We'll tackle that mystery in our next explainer.